Today we're going to be talking about different types of data and different types of representations of that data, so things like graphs. We will also be talking about when some people make these graphs, they can be misleading if not done properly or if not done with the right intent. Two types of data we're going to be focusing in on: qualitative and quantitative. Now, qualitative can also be called categorical data. This consists of labels or non-numerical entries. Basically, if I asked everyone in the class, who their favorite band was, the answers I'm going to get back are not going to come in the form of numbers. They're going to come in the form of names. So that would be non-numerical, qualitative, or categorical data. Now, when using qualitative data, operations such as adding, finding a mean, finding the median, these things don't make sense, okay? So we use different types of measurements when dealing with categorical or qualitative data. Quantitative data is data that's going to come in the form of numbers, okay? And it's going to represent very specific measurements. So down here, we're going to say whether each is qualitative or quantitative. A, the prices of used cars at a dealership. Those are all going to take the form of numbers, so this would be quantitative. Next one. Jersey numbers on a basketball team. Well, that's kind of a difficult one because while they are going to take the form of numbers, when we talk about these actual players, is the number 5 player really only half as good as the number 10 player? That's not really true. So even though this comes in the form of numbers, what it's actually getting at is more of qualitative data. Now, that can be an easy place to get confused. So make sure you're careful. Make sure that when it does give you numbers, these are numbers that are actually increasing in a way that's actually counting something and not just a number to represent an idea of, I like the number 10. Okay? Lengths of songs played at a concert. Okay, this is definitely quantitative. Okay, each number represents a specific length. A song that's 2 minutes long is twice as long as a song that's 1 minute long. These are real numbers that mean real numerical things. Zodiac signs of all the students in class, that's going to be qualitative. That has nothing to do with numbers. Okay, so this is just identifying whether or not our data is quantitative or qualitative. Now, qualitative and quantitative data can be collected from the same data source, such as we see over here to the right. You can use these types of data together to obtain more accurate descriptions of a population. So for instance, if I'm getting information from a student, if I'm asking for quantitative data, I could ask them, how much money are you earning at your job? A qualitative question would be, what is your occupation? Now, both of these questions give me more insight into that student and what's going on with them. If I'm getting things from a house, how many square feet is the house? Also, what city is that in? Now, the city being the qualitative, because Chicago can't be represented by a number. But once again, both Chicago, the location of the home, and the size of the home both give me information that give me more clarity as to what I'm talking about. Now, down below, I've got inserted several different types of graphs that we might use to represent our data. Now, the first one is a bar graph, not to be confused with a histogram. Now, a bar graph I'm usually going to use with qualitative data. Okay, so each of those bars might represent something different, but something qualitative. Like if I asked everybody what their favorite food was, the first bar might be pizza, another one might be hot dogs, another one might be Italian food. It could all be different measurements, but just because one appears before the other doesn't make it greater. We also can't do anything like skewed or symmetric because it doesn't make sense in that situation. Circle graphs are also a great place for qualitative data. Now, what I'm going to do with the qualitative data here is each pie is going to represent a very specific percentage of whatever the responses were. So if 1/4 of my respondents said they prefer pizza, then that is going to take up 1/4 of my pie graph. A line graph needs to be quantitative. And aside from quantitative, it's also going to have something we haven't dealt with much yet. It also needs two variables. So I'm going to not only have just numbers as responses, but I'm going to have two distinct sets of numbers that go together in order to make a line graph. Okay? All these others have also been one variable. Now, this next one is the histogram. This is what we did in class. It shows how often something happens over specific intervals. Now, these intervals are going to be numerical, so this one is as well quantitative. It is also only going to use one variable. Okay, so I'm only receiving one grouping of numbers, and all of those numbers represent the same kind of thing. Stem and leaf plot, it orders numerical data. It kind of gives us an image similar to what a histogram does. Now, each of these stems, so like stem is the one, you combine it with the leaf to create the number. So what this really stands for is 10, 12, 13, and 16. And that's what a stem and leaf plot does. Stem and leaf plot is also going to be quantitative. And one variable as well. Box and whisker plot is quantitative with one variable. We use it to normally show the variability. It's our 5-number summary that shows us how the data is distributed. Dot plot, similar thing. This is a numerical quantitative graph. It only uses one variable. Each time you see a dot repeat, that just means that number happened that many times. So this data set could represent 1, 2, 2, because I had 2 of those. Then I'd have 3 3s. And then I'd only have 1 4. But that's how the dot plot shows it. Scatter plot is also quantitative. And it's going to be 2 variable. Okay, one is going to be our x variable, one is going to be our y variable. All right, so now that we've seen these different types of graphs that we can use to represent things, let's take a look at some data and think about what graph would actually tell us what we want to know the most. So look at this eye color one up front. Notice all of our answers were colors. So I'm not going to be using something like any quantitative graph. I need to look at my categorical data. And I think probably what I'm looking for is kind of what are those more common eye ones. So 2 ways I might go here, a bar graph or a circle graph. both will kind of give me similar images, but with a circle graph, I'm going to get a far greater idea of what percentage of people, what fraction of people have that particular eye color. So I'm going to go ahead and put right here, circle graph. Okay, that's why. And for my reason, I'm going to see the ratio of eye colors. Ratio just being how many brown do we have as compared to how many blue. And it's going to be nice and easy to see in that circle graph. All right, next, speed of vehicles. We've got nice numerical data. Now, I don't really have this 65. It's not necessarily linked over to one of those numbers in particular. We don't see a pairing of numbers happening. And so because of that, I'm not going to use any of my two variable data ones. I'm really just comparing two groupings of numbers here that came from different sources. So what I might choose to do here is something like a box and whisker plot. That could be a good one. The stem and leaf plot, kind of cumbersome to make here, and I don't know that I'm really going to be able to compare two data sets easily using two different stem and leaf plots. A histogram might also look nice, so I would be thinking more either histogram or box and whisker plot here. Box and whisker plot is probably going to do a better job of, in a very small amount of space, showing the distribution. Especially if some of that data comes out to be skewed, the box and whisker plot is going to show that a bit nicer. And so I would put dual box / whisker plot. Okay. It's going to show variation and easy to compare. Think about some of the dual box and whisker plots we've done recently and how easy it is to see how one group is so much higher than another, and what fraction of what group is bigger than what fraction of another group. And so that's what a box and whisker plot would do. Although if you said histogram, I think that as well would be a decent, it would have to be a dual histogram where we put one histogram directly above the other. Okay, next, misleading graphs. People use statistics all the time to lie and to give false impressions. So here are some of the ways that they do it. Sometimes they do it on accident, sometimes more on purpose. So a misleading graph is a statistical graph that is not drawn appropriately. This may occur when the creator of a graph wants to give viewers an impression that results are better than they actually are. Below are some questions you guys should be asking yourself when analyzing a statistical graph that will help you recognize when a graph is trying to deceive or mislead. So in other words, here's one way. Does a graph have a title? If it doesn't have a title, really the titles are there to very clearly tell you what the graph is about. Okay, they might not be trying to be too specific so that you start inferring things that it may not actually be saying. Are the numbers on the scale evenly spaced? That is a huge one. People will manipulate the way the numbers are put on there to make results seem bigger or smaller, whatever they want to try to show. Does a scale begin at 0? Now, they also say, is there a break? Now, if there is a break, the guy's still trying to be more honest, but if it doesn't start at 0, they may still be trying to imply some results are bigger than what they are. Does the graph need a key? In other words, if like, for example, a circle graph. If I've got my little sections of the pie and each section of the pie is a specific color, clearly they should be labeling what those are. Are proper labels there? Is everything clearly identified? Are the axes or sections of the graph labeled? So are they telling us what the x variable represents? Are they saying what the y variable represents? Do you understand what each number in it represents? Are the components of the graph, such as the bars, the same size? And so sometimes what people will do is they'll manipulate it, make a bar wider, and so yes, it's going to the right height, but because they manipulated it, made a bar wider, it looks bigger to the eye, and they're trying to make it look like the effect of whatever they're looking at is bigger. So let's ask ourselves some of these questions with these graphs. Describe how each graph is misleading. So one thing I notice right here, we didn't start at 0, and it doesn't contain a break. You can see a break over there. That's what a break looks like. This guy is saying, okay, I'm not starting at 0, but I'm telling you this didn't start at 0 so you don't get confused. Now, the reason why that's a problem is this bar right here, if I was just looking at it, and this is talking about average cost over time. So how much has the cost of college gone up? To me, it looks like, if I don't pay attention to those numbers super well, that from 2007 to 2010, costs of college have doubled, because that bar is nearly twice the size. But that would only be true if we actually started at 0. Yes, it's gone up, but it's only gone up about 3,000, not 30,000. And so that 0, because it doesn't start at 0, each of these changes and how much the cost of college has gone up looks dramatically bigger. It looks like the cost of college is increasing far faster than it actually is, the way that this is made. Over here, yes, we do have the break, and it is starting at 0. We can still suffer from the same thing. Now notice, this only goes from 8.9 to 9.06. And so even though that looks like a line that's going up really fast, it's not. It went from an 8.9 to a 9.06. It barely went up at all. And so that's one thing, that because they don't have everything starting at 0, not really, it makes us feel like the effects are larger than they are. Next is, you notice they go up from 0.9, 0.92, 0.94, 0.96, 0.98, and then we're up at 9, and then it starts counting by 0.01, 0.02. So it suddenly started changing how it was counting. Now what might be happening here is this person is trying to make it look like things are increasing far faster here than they were here or here. And they might be doing that to try to say, oh, the hourly wage is increasing really fast. It's going up really fast, and the government doesn't need to get involved. Don't get the government involved. Don't have them try to increase minimum wage. It might be necessary. They're trying to lie to make it look like more increases are happening than are actually happening. Okay, you guys are now ready to work on your assignment. Spend the rest of the time on that.